Bien, alors nous avons le grand plaisir là d'accueillir ce soir le professeur John Bell, Université du Western Ontario, et qui, comme vous le savez, est un des plus éminents spécialistes de théorie des modèles, de théorie des catégories, des réflexions philosophiques sur le continu, d'analyse non standard, etc. Et John Bell est invité pendant un mois, jusqu'à la fin du mois de mai, au CREA. Et donc, si certains d'entre vous ont envie de discuter avec lui sur un certain nombre de sujets, organiser des rencontres informelles, il a beaucoup de disponibilité et je crois qu'il serait très content de profiter de son séjour pour discuter avec certains d'entre vous. Alors, vous vous souvenez, enfin, en tout cas, nous, génération, là, se souvient de son premier grand livre, là, avec Slumson, qui était une bible sur la théorie des modèles et de trois produits, de son cours en logique mathématique, et de Toposes and Local Set Theories, son introduction là, de 88. Et alors récemment, il a publié The Continuous and the Infinitesimal in Mathematics and Philosophy. The publisher is
Polymetrica,
an Italian.
But you have to order it.
Yeah.
Very cheap though.
It's on the web.
Yeah. It's a bargain.
And of course,
39 euros.
And of course, it is extremely interesting.
Oh, it goes without saying.
Et donc, ce soir, John va nous parler des modèles de N dans les topoi, des théories constructives des ensembles. Et alors, je signale par ailleurs que John parlera aussi, alors, Andrei, le mercredi 16 mai à 10h30, salle Info 1. Alors, le nouveau bâtiment, hein, voilà, étage -1, sur théorie des catégories et physique. Voilà. So, thank you very much, John, for your presence. And so,
I'll, thank you very much for inviting me. It's a great pleasure and an honor, really, to be here. It's been 30 years or so since the one occasion previously I gave a talk in this venerable institution. I think it was in 76 or something like that, some meeting. So it's been many years. And of course, I'm not going to, you'll be glad to know that I'm not going to even attempt to present my lecture in any French in any shape or form. My command of it is, spoken French at any rate, is minimal, so I'll spare you the potential embarrassment for to be precise, I'll spare myself the potential embarrassment. So I will give this talk in English, but I have some transparencies here, which we've worked out, which seem reasonably visible. And what I really want to do is, I'd heard that this meeting or this series of seminars has been devoted apparently to Poincaré. Is that correct? Yes. Now one figure that I actually won't be mentioning formally this talk is Poincaré, at least not technically, but a number of others will figure in it, including Dedekind and Frege and Peano, who will surface in what is essentially will be a survey talk, nothing terribly new here, on the status and formulation of the natural numbers within topos theory, but presented mainly through the corresponding formal language of local set theory. Now, you won't have to know anything very much, really, about local set theories in order to follow. I'm sure a number of you, most of you do know this stuff, but if you don't, it's not much of a problem because the language that I'll use is really quite straightforward. It looks very much like set theory, and you can use employ the usual symbolizations without running into any problems. The only thing that I suppose would be novel, at least for for classical mathematicians is the fact that the really interesting aspects of this framework that I'm going to be describing and how the natural numbers are presented within it is intuitionistic. So the underlying logic will be intuitionistic, but again, this will only surface occasionally, and it actually does, of course, the fact that the logic is intuitionistic does present certain novel features. As we know, of course, though, the deviation between the classical presented natural numbers and the intuitionistically or the constructively presented ones is not all that great. The real deviation, of course, occurs at the level of the continuum when one gets some much more spectacular phenomena emerging. I don't know. We might have time to discuss a bit, perhaps later, the connection between the natural numbers and the continuum, or the construction of real numbers, if you like, in this framework. But actually, I'm hoping to speak on that, on the continuum and its properties in this framework at another. I forget when it is, but it's in your seminar next week. Okay, so let's just think of first of all, let's think of natural number systems, or natural number presented in the usual sort of familiar, essentially the familiar way, using based on the piano axioms. Now, the idea here is that never mind a local set theory. The idea here is that we have a system in which it's presented in terms of types, although again that's not it doesn't really complicate things particularly. It's just the fact that when you want to introduce an object, it's introduced as a type, just as in category theory an object is introduced as an object. Yes. Now, the usual formulation of a natural number system is presented as a model, if you like, of the piano axioms. I mean, even in the classical framework, we have a type n, or you can think of as a set, if you like, an operation on n, a unary operation s, and then a term, or if you like, you can think of it as an element of n playing the role of 0, and it satisfies the familiar axioms. Now, I've put these turnstiles there because this means that in a theory which is presented in terms of derivability, these axioms are presented essentially as principles which could be derived perhaps from something else, although actually you could take them as being given in axiomatic form. And these are the three familiar principles. You have m and n, thinking of these as variables which are ranging over natural numbers, in other words, of the type of the natural numbers. The first one says that the successor of no natural number is 0. Of course, it's implicit there that n is a free variable, so of course we have implicitly there's a universal quantification there. The second one, of course, is that the successor operation is 1-to-1. It's injective. Sm equals Sn yields m equals n. And then the principle or the axiom of induction, which is, of course, where the impredicativity immediately creeps in. That if you have a set, U, a variable of type Pn, just means that you can think of it as a subset of n, or if you like, it's a variable ranging over the type of subsets of n. Then if 0 is in U, and if for any n, if n is in U, then its successor is in U, then everything is in U. Now, let me just say that local set theories are just the formal counterparts of topuses. They are there's a kind of I'm not going to go into this here, but there's an equivalence essentially between local set theories on the one hand and topuses on the other, and the topuses are essentially the models, if you like, of these type theories, of kind of higher order intuitionistic logic, and sort of inversely or reciprocally, every topos determines a local set theory, which it provides a kind of description of it, and there's an equivalence between these. there's an equivalence. It's not quite a strict equivalence, but it's an equivalence between, if you like, the category of local set theories on the one hand, where the arrows are, the objects are local set theories, and the arrows between them are what are called translations, and this should be familiar to anybody who acquainted with the sort of corresponding idea from model theory or just from formal logic, on the one hand, and the category of topuses, which is not the usual one. The category of topuses usually has geometric morphisms as its, which of course come from topology as its arrows. But here the arrows are what are called logical arrows or logical morphisms that actually preserve the logical structure. And then one has an equivalence essentially up to hand waving, between these two categories. Now, not every topos, of course, actually has a natural number object. It has to be postulated. It's equivalent, of course, or it's analogous to the postulation or introduction of the axiom of infinity in set theory. And just as there are many ways of postulating the axiom of infinity or presenting an axioms equivalent to the axiom of infinity in set theory, so that we'll see there are a number of methods of doing this in the case of the local set theories or toposes. Now, so let me just mention then, before we come to some of the formulations of the ways of introducing. So what I want to do, I should just perhaps sketch it out. I will describe some of the different methods of obtaining the natural numbers corresponding within this frame, within local set theory or topos theory, which will be constructive, at least in the sense that intuitionistic logic will be used. I should mention that the corresponding problem in the predicative case hasn't been solved. There are at least at least I haven't been able to solve it, which may or may not indicate that it's a difficult problem. But so when one says constructive or here, I really mean just intuitionistic. The predicative case where which was of course the thing that interested Poincaré. So Poincaré, I will mention Poincaré. I don't, at least in trying to find kind of predicative formulations of all this is difficult, and I don't. At least it hasn't been done, I think, in this setting at any rate. But we can come back to that later. So after that, I will present or describe some of the features of the natural number system, which has rather novel features, in particular, sort of generic toposes. In the free topos, which is the kind of universal sort of generic model for constructive mathematics in this sense, it's the sort of minimal model. In the effective topos of Martin Hyland, introduced some time ago by him, in which every function is essentially recursive, and then finally in the smooth topos, where every map is smooth, and it's these three toposes: the effective, the free topos, the effective topos, and the smooth topos. So there are various examples of smooth toposes, but these are really the three most important types of topos. The first provides a kind of minimal model. It has the least ontological assumptions, right? It's the freely generated topos essentially over a natural number system. The effective topos in which is realized the principle that every map is recursive, so you're living in a kind of recursive world, the world of if you like, of computability, and then the smooth topos in which you're living in a totally smooth arrangement. And these are the three most important generic sorts of toposes. Of course, there are there are lots of others, of course, but these are the three main have this sort of canonical character. Okay, so let me just mention to begin with then, if I can find the chalk. I'll have to do a bit of chalking here, if I could. Yeah, this is okay. Some of the properties about the natural numbers in sort of curious properties. The general properties of natural numbers systems in general hold. Hold in general in so, or if you like, equivalent just in local set theory. Of course, or principles that one might expect to hold but don't. So one example, of course, is that although the acts of induction, principle of induction, of course, holds because it's given axiomatically. On the other hand, the least number principle. So natural number. Let's just call it n. The least number principle, which of course says that effectively that if you define equal to or less than in the usual way, then that with that relation, the natural numbers are well ordered. This doesn't hold. In fact, you can show the least number principle is actually holding is equivalent to the law of excluded middle, which is a very well-known result. That's right. That's right. So of course, I mean, on the other hand, the form of the least number principle for decidable subsets is provable. So there's a weaker form of this, which is always true, but the least number principle for, let's say, detachable subsets of n is provable. And by detachable, I just mean, by detachable, I simply mean that it's decidable whether something's in there or not. So X detachable means that it's either in or out. This result, of course, is not peculiar. It's sort of interesting, perhaps, just to mention the history of it. It's a very well-known result. But, of course, this was proved originally for, in intuitionistic mathematics, probably by Kleene, first of all. I don't know, ages ago. And it's sort of messy to prove, but you can prove it. And then before the connection between local set theories, or the internal language, you'd like to put it that way, was worked out by various people, Joyal and others, and Benabou and others in the 1970s. This principle was proved by rather hard diagram chasing. I mean, in the old days, you did a lot of work a lot of the work that was later taken over by this formal language was done by just hard diagram chasing, and it's not very easy to prove this in a topos by diagrams. But on the other hand, you can just take the proof that was produced long ago in intuitionistic mathematics, and then simply transfer it, of course, to this framework, and then you get this result. So other features of the natural numbers, which are, well, one quite nice thing, I just mentioned it here since there's perhaps a little, this is sort of Cook's tour of these things, and I might as well mention one principle I like is the formulation of the least number principle, which I call the gap reducing principle, and it's got a very nice formulation actually within truth trees, and I sometimes teach it to students. Is this that if you have 5, 0, and there is an n such that not 5n, so you have so here we have some property. This is I stated this in terms of sets, but here we'll just talk. It's easier here to talk about properties or formulas, if you like. So if 0 has the property, and if there is something that doesn't have the property, so you have a gap, if you like, between this n here might be very big, then that implies that you can reduce the gap to 1. And this is a sort of familiar form of induction. It's not the same. The point about this form of the least number principle is that it only involves successor. It doesn't use equal to or less than. In fact, this principle too, taken over arbitrary properties, is also equivalent to the law of excluded middle. So you're not going to be able to have that one either. Another feature that there are other features of the order structure of the natural numbers. For example, which I just mentioned briefly, for example, that it might be complete. Well-ordered sets, of course, are complete in the sense that every bounded, well, in this case, that every bounded subset has a supremum and infimum. And again, that assertion for the natural numbers isn't equivalent to the law of excluded middle, but it is equivalent to this one, the law of excluded middle for for negated statements. And this is another curious feature of the order structure on the natural numbers. All right, so let's go to look at some of the equivalent formulations of the natural number system. So, yes, this is just some jargon here. You don't need to worry about that. But as usual, I don't know what that 3 is. Unfortunately, when I printed this out, the symbols, some of the symbols got garbled, so I had to write them in. But anyway, as usual in a formal theory of natural numbers, we have 0 already, and then we introduce the numerals, right? That for each that's supposed to be equal to or greater than 1 there. The nth numeral is defined recursively, sort of externally in the usual way, that n is the successor of n minus 1, so forth. So these are the formal, as usual, the formal representatives within the theory of the natural numbers. And then it's very easy to show independently of it. Doesn't use classical logic or anything. Nothing here does. Just shows how close of course, the construct or the intuitionistic theory is to the. It's one way of illustrating the sort of closeness of the intuitionistic theory of the natural numbers to the classical theory. This one didn't get changed. That's supposed to be, those boxes, I missed them, it's supposed to be derivable. That if you have a formula, in fact, it's equivalent, of course, to the principle I wrote down. This is just the usual induction principle that if you can prove alpha from 0, and if from alpha n you can prove alpha the successor, then you can prove for all n alpha n. And that's just easily shown, as usual, to be equivalent to the induction principle as formulated in terms of sets. Now, more interestingly than this is when we come to recursion, and of course it's typical in at least in the category theoretic formulation of the natural numbers to formulate the idea of natural numbers in terms of recursion, because of course that's defined in terms of maps. Well, you can prove in the usual way. It doesn't require, again, any use of classical logic. If you have a natural number system, then as usual, you can prove this recursion principle that if you have any set of, well, this is, again, because of the type theory, but for any set X, okay, you see, sets have to be of power type in this theory because you have individuals. But anyway, that doesn't matter here. For any set X, any element of X, really, any term of actually there's anyway any element of X. I say closed term, but any element, and you have a map from X to X, then you can do recursion on that, simple recursion principle. So there's a map, a unique map from n to X, which is such that its value at 0 is the given element, and the value of f at the successor of a natural number, immediate successor, is just the function g, the given function applied to the value at n. Now, it's rather simple to deduce from this. It's a standard thing that once you prove that, then that of course gives you the usual result that natural number systems are determined uniquely up to isomorphism, and that's the step you use to make it. Conversely, you can show that, again, that the simple recursion principle yields the Peano axioms. I mean, you can reverse the process, and in fact, that is the way. That's not the way it's usually done, of course, in the sort of classical form of presentations, but in this context, it's quite natural. It's also very natural of course, in the category theoretic, in the categorical context, so that you could formulate the Peano a structure that actually satisfies that simple recursion condition, which we've shown is the case when we start with a natural number system. The whole procedure can be reversed, and such a thing will give you the Peano axioms, a structure satisfying the Peano axiom. So there's another way of two ways of characterizing the natural number system.
Can you put parameters? I mean, considering.
Yes, you can. You can, but actually, all you need for the isomorphism is just this one simple case. Yes, you can. I've only stated it in this simple case because that's all you really need in order to go back to the natural number system. If you want to build with parameters, you do the usual kind of thing by enlarging the, the set in which you could put parameters in the function g there. Now, if you start off with a oh, I forgot to change this too. That zero thing there shouldn't be. Anyway, if you're given, so you're given such a theory with a natural number system, and you then take the, this is the corresponding the set n, and you take the map S, and you take which is the thing corresponding to the successor, which is the successor map, and then you take the you look at the map that's, you see, the trouble is this was actually based on on a course that I did using the local set theories. But anyway, if you simply take, just to cut all this short, if you take a natural number system, of course there's a standard way, of producing an isomorphism between n plus, the coproduct, if you like, or of n with 1. To n, so that n plus 1 is isomorphic to n. The standard way of doing it, of course, is just to move, just to use the successor map, and this will give you an isomorphism, if you like, between the natural numbers and the natural numbers starting with 1. And if you write that out in the appropriate way, that gives you, it's an isomorphism between n plus 1 and n. Now, conversely, as is very well known, if you actually have a set X with an isomorphism from x plus 1 to x, then you get a natural number system. This is Dedekind's method, of course. I mean, effectively, it's what Dedekind did in his construction with the natural numbers. At least it boils down to that. And although this procedure can also be carried out, you can carve out a natural number system from this sort of setup. Again, it doesn't require classical logic. It's just completely canonical. It was originally done by diagram chasing, again, before the internal language and local set theory and so forth had actually been invented by Peter Fried very long ago. It's an old result. And he established this within the topos setting, within a category setting, that if you start off with what you call an infinite Dedekind, call it a Dedekind infinite object, that is one that has the property that it's isomorphic to itself plus 1, then you can carve out a natural number system from that. And of course, this is done in the standard way. I don't need really to go into the details. You just do the what essentially Dedekind did, except Fried had to do this, of course, by diagram chasing, which was much more complicated at that time. You get the chain of the element. That's what you do. You take the least thing that's closed, this zero element is the image is in U, and it's closed under the operation of F. And the least thing, that's essentially the chain, and it's the intersection of all those. And then you show, as usual, that in that case, the result, U with F, and the image, which is the 0 there, is a natural number system. And that really is essentially Dedekind's construction. Now, I think one particularly interesting thing, although again it's not, it's very, very well known, but I think of real significance. The natural number systems have the property that they are discrete or decidable. And in fact, the natural number systems are the kind of generic example of a discrete object within a topos. Many toposes, of course, most objects are not usually discrete. I mean, in the following sense. We call a set discrete, or decidable, if you like, if it has the property that, I've just got it for natural numbers here, so that's one. That's okay. So let me write it out here. So X is discrete if its elements are distinguishable, right? That if for every X and Y in X, either X is definitely equal to Y or definitely unequal to Y. And in general, of course, objects treated constructively don't have this property. For one reason, many do, but the natural numbers does have this property, and of course, it's proved by induction. This is again, it's not very difficult to prove it, but it is a striking fact that in some way, even within contexts in which one might have smoothness or elements are kind of smeared out, or the natural numbers, just from those from the axioms, one can prove that they are discrete. And indeed, of course, this is something that's not very remarkable in the case of a classical system, but it's very important in an intuitionistic one.
John, I'm right in thinking this also has consequences for the topological structure of the objects in the topos. I mean,
oh yes, I'm going to
coverings.
That's right. I'm coming to that.
So,
yeah.
Okay. Yeah. It's the so-called decidable subobject.
Yes, it's of course then the fact. Well, they're two. I mean, they're really two important, discrete objects. I mean, one is 2, consisting of 0 and 1, which is the one that measures, maps. The non-existence of maps to that, determines that is a sort of measure of the cohesion of the space or the connectivity of the space. And the other, of course, is the natural numbers. Anyway, I'm going to come back to that later on. Now, I think of some interest, perhaps, and perhaps less well known, since it was my since it's something I did some years ago, and so very likely to remain obscure, is the Frege's construction of the natural numbers, which has come under some scrutiny in the last, I suppose, 20 or 30 years, mainly by philosophers, of course. This sort of called neologicism program, but anyway, some rather interesting work was done. It has been done, I think, in the re-examination, if you like, of Frege's construction of the natural numbers. And I was able to show about 10 years ago that, in fact, Frege's construction, formulated appropriately, is constructively equivalent to the postulation of of a model of the piano axioms. Now, if you do this in ordinary set theory, it's still an interesting result, all right. It's essentially what Frege proves, although in the Grundgesetze, but of course the Grundgesetze was based on an inconsistent. He had an inconsistent principle, the basic law 5, which he used in order to get the result. But you don't need that. You can isolate what if you like the core of the argument in such a way that you can fit it into this framework. So let's just see how it goes. If we're given a local set, well, again, first of all, we want to define the idea is that in Frege's setup, what you actually have, he had objects, he had concepts and objects, and the idea was it sort of boils down his framework. His construction of the natural numbers boiled down to the postulation, right, of a map from the concepts to the objects, which has this property. For him, two concepts, the map, it boils down to it saying that the map assigned takes the same value on two concepts if and only if those concepts are equipollent, that is, if they can be put into one-to-one correspondence. And this is the way, essentially, he gets the natural numbers. Well, I showed it's possible to do all this in a way that's nothing to do. You don't need classical logic, it comes out. There's a sort of canonical construction. So what you do is the basic setup here is what I would call a Frege structure, and that consists of a set within this framework. With a map, and I'll make this definition. First of all, we define what we mean by a family of subsets of a set to be inductive. Now, there are many ways to term inductive. This is yet another, unfortunately. It's not the same as the being inductive in the Zorn's lemma case. But anyway, so I'll just use the term inductive. That if it contains the empty set, and it's closed under unions with disjoint singletons. Now, why disjoint? What you're trying to do is capture the idea of the finite subsets, right, of E. The finite subset should have the property, they should be the least family of subsets that contains the empty set. And there are various ways of doing it. Kuratowski said, well, it closed under the union of pairs of subsets. That's one way of doing it. That's his 1922 definition. Or closed under addition of singletons, that is, adding one new element. Well, if you want to do this, well, and the least such family should be the finite subsets, right? But here you have to be a bit more careful because you can't just add arbitrary singletons here. Why? Because what you want are the finite subsets that are actually discrete. If these are going to be, if you like, correspond to natural numbers, then the finite subsets in that sense have to all be discrete. Whereas if you actually take, let's say, a set that you know to be finite, let's say X, and then you have an element here, let's say A, and you're not quite sure whether it's in or out, right? You don't know. Then how do you know when you add A to X that the thing is still finite in this sense? It might not be. I mean, that A might not be completely distinguishable, you see, from the elements of X. So that's why you take union with disjoint singletons. And this will preserve, if you like, the discreteness of the sets that you're considering. So the condition is that for every member of F, and for every X that's definitely not in big X, then you can, the result of adding it to big X is still in F.
Set difference makes a sense in implicit logic.
Sorry?
Set difference.
Oh, yes. It's all this just means that X is in. It's just an abbreviation for that. Yeah, it means it's definitely out. Of course, in the classical case, you could do cases. It's either in or out. In the case it's in, it's trivial, and in the case it's out, right? You get this, but you can't do that here because you don't have the law of excluded middle. Oh no, it is just the same definition. It just doesn't have the same properties, of course, as the classical case. Yeah. Now, Frege structure, then, this is the setup for Frege's. Well, it isn't his original setup, but it's the one that all that you require here. Is you have a set E, a pair consisting of a set E together with a map into E, and the domain of which is an inductive family of subsets. In other words, it contains at least these finite subsets, and has this property. That nu of x, the number assigned to x, so to speak, is equal to the number assigned to y if and only if x and y are equipollent. Now, it's a pretty argument. At least I think so. The JSL thought it was nice enough to publish it some years ago, 10 years ago now. You can show that if you start with a Frege structure, you can always carve out a subset of n, right, which is the domain of a natural number system. In other words, for which you can prove the Peano axioms. This is the constructive version of Frege's theorem, essentially what he does in the Grundgesetze. Of course, in his case, the map that he has, that Frege uses, is defined, the thing I've written new here, is defined on all subsets of E. You see, but you don't need all subsets. You only want to get natural numbers, so you only need finite ones. Anyway, so... No, that's no. That isn't the inconsistency. It's the inconsistency was having the original map, what he calls the extension map, defined on all possible concepts. He gets the map nu from that. But if you just postulate that, that's fine. But you don't even need all that. All you need is if you may. Recall that Frege's I mean, even when it's cleared up, he gets so-called numbers for arbitrary sets, but they don't have any structure. The only interesting numbers he gets are the finite ones, or the finite ones plus omega. That's why Frege's construction couldn't really be used for transfinite numbers. It just doesn't give a structure to the to the higher numbers. Although Frege remarked that, I mean, this was of course before Russell pointed out to him that his system was inconsistent. But he did think about this, apparently about this idea of introducing infinite numbers, but it doesn't come from his structure at all. Anyway, so I won't go into the details of how this is done, but it's quite a nice construction, and it fully realizes Frege's idea, I think. And then conversely, you see, you can't go from a natural number system to a full Frege structure. A full Frege structure meaning one where the map is defined on all possible subsets. But you can to a Frege structure in this sense, or the finite sense. If you start with a natural number system, you can then reverse the process to get a model of the to get a Frege structure in which the domain of the family, the inductive family, just consists of those that are of sets which are equipollent, if you like, with the initial segments, right, of the structure. That's what that thing is there, that G. So the domain of nu is the family of finite subsets of n, and nu assigns to each such subset the number of its elements, and that's a Frege structure. And you can go from one to the other. It's an equivalent way, if you like, of postulating the natural numbers. Now, I do think, again, if you think about it, it's sort of interesting in the intuitionistic context, because just postulating the existence of cardinal numbers, which is what Frege is doing essentially, is enough to enable you to extract, if you like, a discrete structure, to extract the natural numbers. And all these routes still lead to this, right? To this. Well, of course, they lead to isomorphic structures, but in particular, they lead to structures that are discrete. Now, I'll briefly describe how the notion of natural number appears categorically, because it's historically very important. It starts with, of course, with Bill Lovier.
So G of n is the interval between 0 and n.
Sorry?
G of n is the interval between 0 and n and -1.
Yes, that's right. That's right. Yeah. It's the initial, I mean, it's the initial segment with n, yes. I've just defined it recursively there, yes. If you have a topos, and this was, of course, the original formulation of the natural numbers in topos theory, it's called known as the piano-Lovier axiom. Given diagrammatically, the simple recursion principle that I stated before can be formulated in a topos using arrow diagrams in this form. So if you have you're given this thing up at the top there, right? There's a natural number system. That thing there, 1 to n, is the map that carries the terminal element to the 0. S is the successor operation. So this got shifted over. And then the diagrammatic form of the simple recursion principle just is that if you have any map, you have any element of x, or any map from 1 to x, and then a self map from x to x, then there's a unique map f from n to x such that whole diagram commutes. And that's the piano-Lovier axiom. That is the original form in which the natural numbers were presented in toposes long ago by Bill Lovier. Now, so a thing satisfying that condition is called a natural number system in a topos and a natural number object. And again, so it follows, topos has a natural number object if and only if it contains an infinite object, right? An object which is isomorphic to 1 plus itself, or, if you like, if and only if it contains the corresponding category theoretic presentation of a Frege structure, which could easily be written out also in diagrammatic form. So in fact, we then have, just to, in a sort of conclusion, we have Okay, I could just state it. We have 4 different ways of introducing natural number systems within this, intuitionistically, if you like, within either topuses, or if you like, in local set theory, or another way, intuitionistic type theory, which you could use another term that's used for it. The first is, of course, the postulation of a model of the piano axioms. The second is a postulation of the model of the is a structure satisfying the simple recursion principle. Right? The third is Dedekind's method, essentially, of introducing a Dedekind infinite object from which you can carve out a model of the piano axioms. And the fourth is Frege's construction of the natural numbers for a Frege structure. Of these 4, I think the first 3, of course, are well known. The Frege case has only recently become known, although now it's now pretty. I guess it wasn't. Frege's construction of natural numbers wasn't mentioned for quite a while. But it's nice to see that it's back in its proper, what has assumed its, if you like, its proper role. Okay, now I want to. Sorry.
What corresponds actually in top from previous observation? Yeah, I see that it follows, but what? I mean, in this construction, piano Levier action, we don't have reversible errors, don't we? Right?
No. You have to. No, you have to show that you look at in a. There are 2 ways you can do it. Either you look at the construction, from a natural number object in the local set theory, and then you translate the whole thing, into diagram. It's messy. That's what Freud did.
So it's not something obvious.
Not in a topos directly with arrows. No. I mean, the whole advantage of working with the local set theories was that it removed a lot of these rather complicated diagram chase arguments. It's not. Of course, it depends on your taste. I wasn't a category theorist by origin, of course, and so I tend to think much more. I started really as a set theorist, and so I tend to think much more in those terms. On the other hand, there are some places where there are places where the diagram argument is very natural. There are others where it isn't, or it's just a big mess. It depends. One of the great achievements, of course, of the of the internal language was that it made these arguments very simple. Some arguments, are naturally presented in arrow form, and others aren't. I mean, depends, isn't it?
You have to wax.
Yes, exactly. So,
to the wizards.
yeah, I mean, look, it's a question of really whether. Some of the diagrams are nice ways of writing equations. Other times, if you look at the group axioms, it's rather obvious and it's simpler to understand, let's say, commutativity, because it's just local. It's a simple equation. It depends, really. And in this case, it's certainly much easier to do it by. If you look at Freud's original paper, it's quite long. I mean, it's in the Bulletin of the Australian Mathematical Society for 1970. It was the first very interesting one of the first interesting systematic works on toposes, called Aspects of Topoi. Long paper, I don't know, 60, 70 pages. Okay, now I just want to look at some of the, continuing with this tour, of some of the features the natural numbers take in particular topos as well. I mean, in these sort of important particular cases. Let's look at the free topos. Now, the free topos, I just say, the theory that generates it is very simple. It only has the language, apart from the basic ingredients of these languages, which has to have a truth value object, things corresponding to power types, Cartesian product types, and a type for a type for one, that is a type which only has one element in it.
It's a type theory.
Yes, it's a type theory, a very simple one. It only has those operations, but plus the natural number, right? It has a type of natural numbers. The really free, the minimal topos free doesn't have natural numbers either. I mean, but usually when one says free topos, it includes the natural numbers. So you look at the theory that just starts. The only axioms of the theory, the particular axioms, are just the piano axioms. And you look at that theory. I mean, that's the theory that's the weakest theory, if you like, that contains a natural number system. And the corresponding topos, well, it's important for the following reasons. This theory is important. It's an initial object in the category of local set theories with a natural number object. It's the minimal one. You can inject it into any other one.
You reformulate your action by giving of sequence.
Yes. This is usually given in terms of sequence. Yes, I'm sorry. I didn't want to go into all that. Yes, these are sequence. Yes, quite right. And the corresponding topos is called a free topos. It's the initial object in the category of toposes with natural number objects. And so it has a special role. It's been claimed, for example, by Jim Lambeck, who's for years been saying it's the place where intuitionists and classical mathematicians and constructive Platonists can all get along. So he says, because it has, it exhibits, if you like, nice aspects, some aspects of all three of these positions. However, be that as it may, it's certainly a very nice theory, and it does have some, and the free topos and the corresponding theory. See, these would be in a way, it's the minimal theory for well, of course, it's impredicative, so it doesn't satisfy the stricter conditions that are imposed on constructive type theories, but it's the kind of minimal theory that you need in order to be able to do constructive mathematics. It's the one that makes the least assumptions. So it has nice, if you like, philosophical properties, so to speak. Now, as a matter of fact, proving that the particular principles that I'm going to mention here about the free topos or the free local set theory, they're not easy to prove. For example, one principle I just mentioned here, one would expect, although it's not so easy to prove, and there are a number of ways of doing it, though. For example, one would expect that one would have the disjunction principle, because one surely expects that for a constructive theory, that if you can prove a disjunction, these are sentences, alpha and beta, of course, being sentences, then you can prove one or the other. Now, of course, we know this is true for intuitionistic logic. It's true for intuitionistic arithmetic, and it's also actually true for intuitionistic let us call it intuitionistic type theory, free intuitionistic type theory. But it's not very easy to prove. Also, another principle you might well expect to be true, which is given the constructive interpretation of the quantifiers, is if you can prove this. Well, let's just do it for natural numbers. That's the easiest thing. That if you can prove there exists n phi n, then you can produce a specific instance for which that's provable. Again, none of these principles that are would you certainly you'd expect them to hold. It would be unfortunate, right? Indeed, if they didn't hold, because then sort of basic principles of constructive reasoning would fail to be satisfied by this free topos. But they do hold. Much more interestingly, though, there are many more powerful principles of constructive analysis or constructive mathematics that have been shown to hold in the free topos, that are closer, in fact, to Browerian principles, or at least the formulations of Browerian principles, later formulations of Browerian principles. For example, you can prove the principle of choice. Of course, in the case of natural numbers, because classically it's well ordered, you can always prove, if you have, for every natural number n, there is an x, say in some set x such that phi n x, then you can prove that there's a number, a natural number, a function from n to x that for all n phi fn. Well, of course, that's sort of trivial in the case of the natural numbers construed classically, because you can just choose the least one as your value there, right? Sorry, that's the other way around. At any rate, this principle for the natural numbers is something that's provable in the case of the in the free topos. So the choice principle holds, and also the natural numbers actually satisfies a much more powerful condition, namely what's called the uniformity rule, that if you have, this was one again that was suggested by really from thinking about the properties of relations constructively. So if you have a relation between sets, so a family of sets. So the x here is ranging over, let's say, subsets of some set A, and for every x there is an n such at phi x n. There's actually a choice of a single n for which that condition holds for every x. Now, from this uniformity rule, this is a very strong property, and it was proved. The arguments for proving it it's not all that easy to prove. You'll actually find it in Lambeck and Scott's book. They discuss some of these. Their book on topos theory and higher order categorical logic. But one of the most striking consequences of this is that there's a relationship between the natural numbers and arbitrary power sets. That if you take a power set, it's always strongly indecomposable. This is really talking about coherence. There's a tremendous kind of cohesion, if you like, of power sets. Of course, the natural numbers can't be cohesive in this set because they're discrete. But if you go to a power set, you get something that's very, very far from being discrete. It's completely amorphous, some way. It's strongly indecomposable. That if you take a countable family, right, of subsets of PA, whose union is, so you try to decompose it, then one of them has to be the whole of the power set. And it follows in particular that any function, right, from a power set to the natural numbers is constant. Well, of course, that's a sort of familiar notion topology. N is discrete, and functions, if you have a space which is such that maps of discrete spaces like n or even just 2 are constant, that's characteristic of connectedness. So topologically, what this is saying, that as soon as you go to power sets in the free topos, they get this highly cohesive or a character. So you could say strong indecomposability is a kind of extreme version of what you might call the pigeonhole principle. Right? So in a general form, the pigeonhole principle states that if the cardinality, let's say, of M exceeds that of some index set I, then any I-index covering of M has a non-singleton member. There has to be some more than one thing put in the pigeonholes determined by I. So the more the cardinality, sorry, that shouldn't be there. The more the cardinality of M exceeds that of I, the larger must one of these non-singleton members be, of course, sort of intuitively. In particular, it could be M itself. So if we call M incomparably bigger than I, if any I-index covering of M always contains M as a member, right, then you say M is incomparably bigger. And then if something's incomparably bigger than I, then any map has to be constant. And then you can sum up the situation in the free topos by saying that any set with more than one element is incomparably bigger than it. Sorry, that's already the case. In the free topos, or the free local naturalized set theory, any power set of a set with at least one element is incomparably bigger than n. Right? I mean, it's incomparably bigger than, in this sense, than any of the discrete set, and particularly finite set also, but even than n, which is the sort of canonical discrete set. So the free topos is it's very much as Brouwer seems to have conceived the mathematical universe. I mean, you have the natural numbers, and this is discreteness, right? Those are the discrete structure par excellence. But as soon as you go to the continuum, or to sets, or to, if you like, geometric structures of some kind, then they have this property of being very, at least continua have this property of being incomparably bigger than n, and in the sense that the discrete parts of them are really very small.
So you mean that even the power set of a singleton?
Yes, P1. Exactly. Very good. Yes. Yes. True value object already, you see, is so huge. And this is in the free topos. I mean, it isn't in any very surprise. You know, it's in the one that's embeddable into every other one. Of course, that doesn't imply that that's the case for arbitrary toposes, because that's not something that's, that's reflected under logical morphisms. But nevertheless, it's a very striking fact that you appear to have these, these sort of levels. Well, it's something like that. It's a kind of topological version of that. I mean, yes, this power sets, as soon as you start talking about properties, right, even with a single element, the properties blow up, right, into this huge sort of amorphous thing. And in a way, this in some sense does reflect some of Bauer's ideas, I think, although it's one, I think it came as rather a surprise to find these rather more exotic Bauerian principles holding in what is essentially the generic model, right, for constructive mathematics, because nobody expected a lot of Bauer principles don't hold, of course, in recursive mathematics and so forth. Yes.
When is functional, this corresponds to continuity property of morphism, because you get into the discrete set, discrete topology.
That's true, but the fact is, it's by no means obvious that when it has built-in continuity here, it's not like the case of, let's say, exactly. It comes sort of for free. I mean, this is really very remarkable. Yes, that's exactly right. It does come for free. And, well, of course, you can also prove, I don't know how to do it, but Joyal proved, it's said at any rate, that he proved 30 years ago that every map from R to R is continuous. He proved Bauer's continuity principle in the free topos. Now, I wrote to him because he didn't reply to emails. So I asked Peter Johnston, who knows everything about this, if he knew how Joyal had actually proved this. And he said he couldn't remember. Joyal never published it, as typical of him. But that's also a very remarkable fact, which I'll just say here. Yes, you get these continuity principles for free. So, what do we mean by R? Dedekind reals. To find, reals in the usual, say, the Dedekind way by Dedekind cuts. Okay. I mean, that's of course a basic idea of Bauer's, but it actually holds in the free topos. Okay. No, I'm going on. I said it was going to be an hour, so I won't go on much longer. Let me just. All right. Well, let me just say another way of viewing strong indecomposability is the following. Marked at n is discrete, so we call a set which is not discrete. Let's call it amorphous. I mean, for present purposes. So a non-Boolean topos, such as the free topos, all power sets are amorphous. Elements of an amorphous set can be thought of as being only partially distinguishable. They're sort of like elements are like clouds, sort of. The strong indecomposability can then be expressed like that, and the premise construed as an attempt to coordinate each element of M with a natural number. Right? That's the idea. You're attempting to make this coordination. But if M is sufficiently amorphous, there's no way of distinguishing these elements of M so as to make the elements of the discrete set distinct. That means that F has to be constant, and so you get this constancy principle. Another way of thinking about strong indecomposability is seen as a version of strong countable compactness, right? This sort of thing in topology, with arbitrary countable covers replacing open covers. This is a very typical move, of course, instead of working with open sets, you work with arbitrary subsets. And this is sort of forcing spaces to be very, very, very smooth in some way. Okay, so not to go on for too long, but I just mentioned briefly about some of the properties in the effective topos. Now, in the effective topos, which is another basic topos, which interestingly, I should just mention, nobody seems to have decisive axioms for it. I mean, in the case of the free topos, of course, it's automatic that you have these, right? It's just given axiomatically. In the effective topos, which is constructed in a particular way, there doesn't seem to be a completely convincing sort of axiomatization of it. But nevertheless, I mean, that's even so, it clearly does have some kind of a canonical character, because the idea is that every function between objects constructed for the natural numbers, including the rational and the real numbers, is recursive. I mean, that's the idea that's being realized there. If in the free topos you're putting in as few maps as possible between objects, only the ones that need to be there because of the basic axioms, right, constructions, then in the effective topos what you're doing is only really including the recursive ones. Now in that topos, again, we have some interesting features. Oh, sorry. Yeah. Yes, Highlands topos, yes. And worked on by, of course, a lot by Pino Rossellini, who's done a lot. But he says he hasn't found axioms that he's completely satisfied with. So anyway, and then you could prove, for example, in the effective topos that suitably formulated, every function from natural numbers to natural numbers, you can write out it is actually it's a recursive function. I mean, it's for some n, it's the nth partial recursive function, which in this case is total because it's a function defining the whole of n. In the effective topos, actually, again, a curious feature that n to the n, the set of functions from natural numbers to natural numbers, is subcountable. It's actually, well, there's a subset of n which is such that you can map the whole of u, that you can be mapped surjectively onto n to the n. Again, the reason for this is that in effective topos, n to the n consists not of arbitrary maps, but just of the recursive ones. And the subset consisting, the subset u that I mentioned here, effectively is the set of codes of total recursive functions out of the set of codes of arbitrary recursive function, partial recursive functions, which is, of course, the whole of n. Now, I'm going to skip this because I've got some stuff on Russell's paradox here, which I'm going to skip because I'm going on too long. Anyway, so I'll skip that. Yeah. Well, all right, just to conclude, you can show, I mean, just to sum up what I was going to say there, the power set of n and n to the n really are quite different. I mean, we usually, classical mathematics, of course, diagonalization and Russell's paradox, which correspond, Russell's paradox, of course, corresponds to using the power set, and diagonalization corresponds to using the function space, right? They boil down to the same thing classically. They're sort of interchangeable, but they're very different constructively, and the difference is very strikingly presented in the effective topos, because you can show Russell's paradox continues to work. The Pn, the power set of n, is still big. It can't possibly be subcountable, right, in the sense that n to the n is. So it remains large, but it's interesting that n to the n can't be equipollent with n, so it's uncountable in that sense, but it can still be subcountable. So again, it also turns out that in effective topos, as in the free topos, Pn is actually incomparably larger than n as well. So a similar phenomenon actually arises there. Now, finally, I just want to make a few comments on the smooth topos, and I'm running over my time, I know, and I'm sorry about this. I didn't think I had. Okay. Well, all right. So let's just briefly describe. This is the third case. In smooth infinitesimal analysis, again, we just have some axioms that ensure, in this case, that ensure that the continuum, which is given axiomatically here, of course, in the other cases we've mentioned, the real numbers can be defined. Given the natural numbers, one can perform the construction of the real numbers in any of the usual ways, by Dedekind cuts, by taking the power set, essentially. Well, you construct the rationals, and then you could look at sequences in the rationals, Cauchy sequences, or you can do Dedekind cuts in the rationals. You get different results in the two cases. There are several different constructions of the real numbers from the natural numbers that don't yield isomorphic results in general, but you can do that. In the smooth topos, on the other hand, or in the theory called synthetic differential geometry or smooth infinitesimal analysis that's associated with it, the real line is given axiomatically. And of course that makes it quite interesting because you can compare the real line, the smooth real line is given axiomatically, with the other versions of the real numbers given by starting with the natural numbers and performing the usual constructions there. And in fact, that's what this part of the paper was based on, but I'm not going to go into that. Anyway, so there we just have axioms. So let me just say that the axioms for the real line here are given in such a way that they satisfy the. It's an ordered ring, where the ordering is you formulate in terms of a strict ordering, which is typical in intuitionistic settings, and it in such a way that the intuitionistically, at any rate, the ring is an intuitionistic field. That is, if you have something that's an element x which is distinguishable from 0, that is, if x is unequal to 0, then it has a multiplicative inverse. And then these are sort of standard type axes that I don't want to go into. Interesting here are the arithmetic axes, because there are going to be two ways at least in some of the models of this theory of smooth infinitesimal analysis, to define the natural numbers. And one way of doing it is to postulate the natural numbers, or the smooth natural numbers. In fact, the idea is you're given those, and then but of course, there are two ways. You could give some axioms for the natural numbers, and the idea was, well, this was the sort of idea. You take the function, if you take this function sine pi x and look at the, right, and you look at the zeros, and of course this gives you the zeros of this are the natural numbers. But the point is that these can be different from the standard natural numbers. In other words, the natural numbers, the standard natural numbers in the model is just given as the least set, starting, least subset of R that contains 0, right, and is closed under adding 1, and that will give you the standard natural numbers. That would not necessarily coincide with the smooth natural numbers, which are axiomatized by means of these sorts of axioms. And so this is how you could do one way of doing non-standard analysis in this framework. Anyway, okay. Now, of course, the key principle. So we have these axioms for the are weaker than the piano axioms, because the induction principle doesn't hold for arbitrary formulas. Look, this is rather similar to the non-standard analysis case. In fact, that was the idea here, where the induction principle for the non-standard integers, right, holds internally, but externally it only holds for the definable subsets. And a similar thing is going on here. That is, where the alpha there is it's what's called it's a formula that has a particular kind of logical form, and it isn't an arbitrary one. Okay. Now, the really most important principle, of course, in non-standard analysis, that I'm not really talking about here in any detail, is the principle that tells you that the nilpotent elements, the set or the elements whose squares are 0, is not degenerate, and it has the property that any map defined on it it's always just a translation or rotation. It's always affine. This is the key principle of smooth infinitesimal analysis, but I'm not supposed to be talking about that here, so I won't. Now, that's right. Yes, that'll be something for another talk. But anyway, let's just think about the natural numbers in this system. In smooth, you see, the natural numbers plays an important role in it. Doesn't the natural numbers plays almost no role as it stands in synthetic differential geometry proper. Very little. I mean, of course, just as it doesn't really play a major role in differential geometry. I mean, you use it for indexing, but it doesn't really play a central role. It does, though, when one is considering when one considers introduces the possibility of doing non-standard analysis. in this framework. You see, because infinitesimals in smooth infinitesimal analysis are not invertible, right? They're nilpotent, and so they're not invertible. Infinitesimals in non-standard analysis, on the other hand, are. They're essentially the inverses, they're Leibniz type infinite. They're essentially the inverses of infinitely large natural numbers. So that's why the natural numbers, the natural numbers then in smooth infinitesimal analysis plus invertible infinitesimal, or at least in which you can realize Robinsonian non-standard analysis, the natural numbers do play a role that they really come into the foreground. And you can show that it's possible to introduce invertible infinitesimals resembling those of non-standard analysis, and you get another kind of infinitesimal than the invertible ones in addition to the non-invertible ones. So just to finish up, the standard natural numbers, so we have this idea of this axiomatically introduced natural numbers, and then we have the standard natural numbers, which is as we'd expect, it's the smallest subset of R containing 0 enclosed under operation of adding 1. Now the point is you can produce models of smooth infinitesimal analysis in which the standard natural numbers, that's its n thing, is a proper subset of big N. So the members of the complement are non-standard integers, just as in the Robinsonian sense. And the inverses of those, right, are, if you like, Robinsonian infinitesimals. So multiple inverses of non-standard integers are infinitesimals, but being invertible themselves are a different type from the nilpotent ones. And anyway, you make the definition. I did the definition here. That's the formal definition of the standard natural numbers, the intersection of all of the of all inductive sets in the obvious sense, the ones that are closed under containing 0 and closed under adding 1. And then you can define the infinitesimals. To core, right? All infinitesimals. The infinitesimals are then going to be the members of R which are trapped for arbitrary standard integers n between minus 1 over n plus 1 and 1 over n plus 1 for arbitrary such n. Well, of course, that should be familiar to anybody who does non-standard analysis because it's the same definition. Except in smooth infinitesimal analysis, one has in between there, between these the members of IN, non-invertible or nilpotent infinitesimals as well as the ones that are familiar from non-standard analysis. That's the largest infinitesimal neighborhood of 0 in smooth infinitesimal analysis. It includes the non-invertible infinitesimals, and it also includes the Robinsonian ones that are obtained from the non-standard natural numbers. And you can show that invertible infinitesimals are strictly larger than their non-invertible or nilpotent cousins, in the sense that every one of those is, and it's not 0, then it's always bigger than any of the non-invertible ones. And so you have this picture that the non-invertible infinitesimals, which have really nothing to do with the natural numbers, they're defined algebraically, right? That is, they are the nilpotent elements as a purely kind of intrinsic property. The invertible infinitesimals are defined in terms of the natural numbers, and you have to so the natural numbers play an important role in that regard. So finally, I don't think I've got much more to say here. No, I don't. Good.
What about things like topological genus, non-book false, etc.?
I don't know, actually. I suppose one would think that isn't affected, right? You see, usually what happens is that numbers like anything that has this sort of concrete character remains the same. I mean, right? Otherwise, there would be something seriously wrong. I mean, for example, if the Bethe number or something of a manifold turned out to be different in this theory than it did, something would be wrong. But that's not the case, and you can show that for those sorts of things, for numbers, and in fact for standard, essentially for any numbers, real numbers, for example, that are introduced in the usual classical way, and they retain their classical properties. Okay, so finally, and you've been very patient with me. The idea is that the axiom you want to introduce is to say that to claim that invertible infinitesimals are present really is to say that there are non-standard integers are present, and that's the way that one actually does it. And there are various other ways it's often the case that you want to introduce as many non-standard integers as possible in order to be able to perform certain constructions, and you can add conditions to ensure that as well. Finally, there were some remarks I was going to make on the real numbers here, but I think I will leave those. So thank you very much.
So my question is, can it be that you have infinitesimal?
C'est rouge.
So, check out. So, in the last model,
Yes.
you said that there are infinitesimal which are defined as nilpotent elements.
Yes.
But how can it be that in your algebraic system there are nilpotent elements because your real number are not a field, or in what sense are they, or are they not?
Yes, yes.
I suppose it's due to intuitionistic logic.
It is, again, yes. Good question. Yes, it is just this, that you do know, right? Okay. But of course, you can't, I mean, the point is that if... Well, it isn't quite that. It isn't. You can't do that. That's not going to work. But let's put it this way. From this, you can't infer. You can't. The precise way of stating it is this: that you can't from this. Of course, you can't infer that it's 0 or not 0. The argument which won't go through, and so you never get this. So, in fact, the precise way it's stated is this, that if you take, okay, now you can't assert, well, you can assert it, but it would be inconsistent. I mean, you can't, on pain of inconsistency, assert that there's something in here which is not 0. But what you can assert, and what is the case, is this, you can prove. That's affirmable. In other words, it's not the case. But from that, you cannot infer, you can't push this thing through to get a, there is an x such that x is, right? It gives you, it brings it very close, you see, to inconsistency, but it's not inconsistent. You see what I mean? This is provable. You can prove this, and in fact, you can prove. Well, okay. I mean, the law of excluded middle is refutable in this form. Of course, it's never refutable propositionally. You see what I mean? I mean, that's the difference between, of course, between quantified first-order theories and propositional theories. You can't take a propositional theory in intuitionistic logic, right, and extend it in such a way it's still consistent but contradicts classical logic. But you can with a first-order theory, because this implies the failure of the law of excluded middle in some sense. It doesn't imply, well, there is a proposition P such that not P or, of course not. But that's how it works. So in other words, the picture here, yeah, they can't take the quantifier out. Yeah, sure. And this thing here is just it's an object where the only thing in it, well, it's this. Well, it's this. Here we are. Actually, I saw this diagram in the Centre Pompidou. They put mathematical. Did you see? They putting mathematical papers up as and there was y equals x squared. And I said, the generic tangent vector, here it is. So it's the intersection, right, of the parabola with the around the origin. But you can't prove. You could show it's non-degenerate, but you can't prove that there's anything in there apart from zero. I mean, in other words, it has the property that if you think of it, think of sort of this half of it. It's a generic tangent vector. It's got a place you can pin zero on anywhere, but you can direct this in any direction, but it doesn't really have any magnitude. It's a tangent vector. It's like it's a speedometer needle, but without length.
It's one of Barrow's lines.
It's one of Barrow's linelets. I mean, but the thing is that it has all the properties that you would expect. It gives you the first two terms of the Taylor expansion, right? It's the linear part, and it satisfies those. But it's true that it is quite interesting that look, I would just say this is not on the point of natural numbers, but if you want every function to be continuous, if Leibniz had been really serious about this, then he would have realized that the law of excluded middle is bound to fail, because as soon as you have a blip function, if nature doesn't make jumps, then there can't be any instantaneous, right, this function, the simplest possible discontinuous function. Right? Right? It's zero at 1 at 0, and it's 0 everywhere else. Well, that's the simplest discontinuous function you can think of, and it isn't there if every function is continuous. And why isn't it there? The only thing that would go wrong with it would be that it's not a function defined on the whole of the real line, and that means, if that's the case, it means that that its domain isn't the whole of the real line, and that's just to say that for every number, it's not. You can't show that every number is 0 or not 0. So you immediately get the failure of you're immediately in the realm of something like intuitionistic logic if you're living in universal continuity. Of course, I don't think that Leibniz and all the people who thought about logic and that they always seem to have been concerned with the law of non-contradiction. They never thought very seriously about the law of excluded middle. But it's abandoning the law of excluded middle that enables you to do these things. Yes.
It's interesting to know that both André and Grothendieck, when they were speaking about differential geometry, they introduced infinitesimal.
I know.
Well, André was the first one.
Yes.
And then Grothendieck elaborated on that.
Yes.
But there was some other harsh comment by André about non-standard analysis for that. And he seemed to consider that they were incompatible. And so in this sense, it is not incompatible.
No, it's not.
I'm happy with that.
I do think there was a discovery that was made later. There were big developments in. Well, the connection between intuitionistic logic and category theory, of course, wasn't established at all until 1960s.
Yes. Well, but at the time,
Grothendieck wasn't. Well,
no, Grothendieck was never a logician,
and
did not
wasn't
want
very
to indulge in logic. But for the history of geometry, of algebraic geometry, is especially important because, people, as before André Weil and Grothendieck, were very happy with dealing with algebraic geometry with a field of constant.
Yes.
With a field of constant, and then the big jump. To start with an arbitrary ring, instead of a field,
right.
Was made partly for that, not only for that,
yes.
but partly for that, because they wanted to have a possibility of having nilpotent infinities.
Yes.
But if we use the possibility of course of non-standard analysis, then you can have invertible infinitesimal, as you mentioned. But this is quite interesting. It's the first time I've seen that it's possible to reconcile both.
Oh yes, you can do it.
I thought there was
Yes.
There was a course, and you had to choose left or right. But it's interesting that in this framework you combine both.
It's going to combine parts of course, you can't do full non-standard analysis here. There is still a problem of doing non-standard analysis in the Robinsonian sense constructively. Yes, it's true you can sort of do it in this model with this rather limited way. But the general problem of actually doing non-standard analysis in a kind of constructive setting is still open. There's still work being done on that. The principles on which non-standard analysis, the usual construction of models for non-standard analysis are based, are classical. You use the axiom of choice, and you use non-principal ultrafilters and stuff which implies classical logic.
Yes.
So there is work going on now by Ecole Moerdijk and others trying to fit in a more general non-standard analysis. For example, Nelson's internal set theory into something like this more constructive framework, but it's not all that easy. Non-standard analysis. You're right. You're actually quite right. I mean, for most of non-standard analysis, the major sort of the general thrust of it is classical. But it's true. It is possible in this case to reconcile the two. Yes.
Yes, but in a sense, the problem to construct an effective non-standard integral is a basic thing.
Yes.
It's a basic thing.
Yes.
And using paracoherent logic, it's possible. But
well, maybe.
It's not a joke. I mean.
Okay. Well, there is, and you know, Graham Priest was who was one of its inventors. Was my first PhD student. We've agreed to differ ever since. No, I just.
It would be nice to understand what kind of natural number object you're using in this topos, because the effective topos and the topos as you mentioned there do not have the same natural number object. Namely, in general, in Grothendieck topos, if I remember correctly, we're in Cartesian closed categories with countable coproducts, countable infinite coproducts.
Well, effective topos isn't a Grothendieck. I mean, you know.
Yeah, it is not. So the natural number object
is a Grothendieck topos, at least.
I see. So your natural number object is like those. It's not constructed Highland style.
Well, no, that's true. They aren't. There's a different construction. If you trace it through, it's the natural numbers end up, at least the standard ones. No, that's not true. It's these that turn out to be the counterpart of the natural numbers when you trace it through from the base, from the base topos, given the natural numbers. Yes, I'm not quite sure. The natural numbers as given by these internal naturals. Because look, you can show that in most of them, as far as I recall, in most of the models for smooth infinitesimal analysis, there's no difference. I mean, in other words, you can show that the natural numbers, as you just use the standard ones, and they don't really enter into this kind of discussion. But in these models in which you do non-standard analysis, then you have two different ones. Namely, the standard natural numbers are not the ones that arise, right, as the image, if you like, of the natural numbers in the base topos that you start with. Just as in the case that's similar, of course, to the situation with the effective topos. Yes. Yeah. Max, yeah.
In the realm of real algebraic geometry, you find a situation that reminds a little bit like this, but it is perfectly classical. You have, if you work with convex subrings of real closed fields, which is an important object in this in real algebraic geometry, then you will have, invertible infinitesimals. And then non-invertible infinitesimals, although they are not...
They're not nilpotent.
Nilpotent, of course. And as a matter of fact, you can arrange in such a way that you can have as many realms of invertible infinitesimals, which are as many realms as you want. And I would call a realm, or two realms different, if they are Archimedeanly non-equivalent.
Right, yes.
And then you can have as many realms as possible, as you want, of non-invertible infinitesimals. Of course, the non-invertible ones come before, are closer to zero than the invertible ones.
Right. So these are they're infinitesimals.
This is a rather standard situation, actually.
I see. So but those are infinitesimals in the same sense as that I define. The ones trapped between. Between
sure,
1 over n and minus 1 over
sure,
n
but
for n standard some standard natural number. Is that right?
Oh yeah,
they all have to be there. So you have a lot of
sure.
I see. Yeah, I don't know what the connection with there. One of the difficulties with this subject is that it has such a very nice intuitive. When you're working with it internally, it has a very nice intuitive presentation. I wrote a very simple book on it. This infinite, doing basic calculus and basic physics and so on with it. The real difficulty with it, I think, is the effort that has to be put into constructing the models, which are, you really have to. Well, your friend Eduardo Dubuc did a hell of a. It was a major effort, trying to take these very natural principles, right, which are very beautiful, and actually show that you have, construct models that actually do have the right properties, and it's not very easy. And so you have to put a lot of work in just to get some very simple principle, natural principle sort of realized. It doesn't automatically come out. As I say, even in the case, if you look at the book, the sort of systematic work on it, by Reyes and their book, Mordijk and Reyes' book, it's a lot of effort just constructing the thing. Once you've got it, then you have all these very nice, really very nice features emerge. But I think for that reason, it's rather difficult, I think, to then make perhaps connections between the work here and the kind of work, for example, that you are describing, because simply because it's so hard just to get them, to construct the models initially. So I don't know what the connection is there. There's a lot that's very, although in synthetic differential geometry, that is sort of very suggestive, of mathematics naturally in other areas, since it was designed in any case in the first place to do. To realize certain intuitive principles in differential geometry and elsewhere. But I do think it's one of the main problems, I think, that's let's say foundational problem that's left with the theory is how much of classical mathematics do you really need to assume, right, in order to be able to do this? For example, proving each of the statements of synthetic differential geometry are, you trace them through. They are, in the end, translations, right, of classical features that hold in a base topos. You use, if you look at it, there are various theorems of classical analysis that get transformed, and are used to sort of forced to give you the right feature. This, of course, is very similar to, I think, the situation. In other words, non-standard analysis is a simpler case, but of course there you have an automatic transfer principle, which you don't have here. But it is similar to some of the problems which you have in forcing, in classical set theory, where verifying that such and such a property holds in a model reduces to showing that the ground model or whatever has some particular feature, right? And you sort of trace it back to there. And a similar thing arises here. So I don't know what, and again, the real algebraic geometry is concerned, I don't know, nobody really has, I think, has pursued this to make the connections. It's been mostly with differential geometry, of course, because that was what it was designed to do. But connections with other parts of mathematics, for example, real algebraic geometry, or indeed, since ultimately these models arose from algebraic geometry. They were, Lorvier had this idea of thinking about the idea of infinitesimals in Grothendieck toposes, and this whole idea of infinitesimals coming from there that led to this notion. But the actual connection between synthetic differential geometry, which arose really from algebraic geometry, and algebraic geometry proper, I don't think is I don't think it's really been systematically developed, as far as I know. So.
It is striking, isn't it? I think you made the remark, yourself, that in the case of the non-invertible infinitesimals,
they're not really there.
Well, yeah, but also that is really a purely algebraic notion.
Yes,
you're
yes,
starting. You're really starting from the ring.
They're like virtual. They're really like virtual particles.
Yes,
to get a little physics.
But it's very much.
They're not really there.
No. But it's also very much in the Grothendieck spirit that you're starting from the ring, from the classifying.
Oh yes,
ring.
Yes. I mean, and hidden behind all this is a ring.
Yeah.
Yes, just of course all that disappears in the axiomatic, right? I mean, you behind it all really is C infinity rings and
exactly
rings of quantity, of smooth functions and so. But all those disappear, of course. You're just left with the formal features of these in the models, the sort of shadow of them. Yes. But speaking of the infinitesimals, I did want to say I do like the way. In fact, in the second edition of this little book on infinitesimals. It's coming to a second edition by Cambridge Press. It's an elementary book. I had some objections from various philosophers, and very reasonable objections about saying, well, these are potential, and so on. That the infinitesimals here are sort of potential existence and so on. I think virtual is a much better term. They're virtual because you know why? They disappear at the end of a calculation. See, just as virtual they do. That's the whole point of infinitesimals. That was what they were used for. You didn't ever find them, in classical mathematics. At the end of the computation, they drop away. Of course, there was a certain amount of hand-waving, right, in dropping away. I mean, when Berkeley made the objection that you first assume, that Newton assumes, right, that there's a quantity and acts as if it's not zero, for some time, and then takes it to zero. Of course, then it drops away, but it's inconsistent, right? But that's why I think one way of thinking about it is that there's something like, I mean, this is only a metaphor, but it's an interesting one because, just as with virtual particles, at the final reality, you don't see them anymore. But they were there in some sense. Similarly with infinitesimal, and I'll show you exactly how it is. You have a principle. The principle is just this. It's very simple. You can't cancel an infinitesimal. So if you use epsilon as a variable, you can't say, just for a given infinitesimal, because it's not cancelable, it's idempotent. But you can do that. It's universally cancelable. And that's how it disappears at the end of a computation. The computation will involve an arbitrary epsilon, and then you end up with an equation, right, which has epsilon on both sides, and it's true for arbitrary epsilon. That can cancel, and then So the epsilons here behave very much like virtual particles. They're involved in the interaction, but they don't appear at the final. They drop away at the last. Sorry, any more?
I understand you will go back to infinitesimals and continuity at Crea in a week or so.
That's the idea.
Okay. So now, can I be criticized slightly, perhaps, or making more precise, an informal remark you made before about categories and diagrams, saying, well, you can work with diagrams or equations. Well, I think that diagrams have a major role in category theory, namely it is spelling out the symmetries which are implicit in equations. So look, for example, at the natural transformations or even the notional adjunction. When you see the diagram, you see the symmetries. Of course, they were implicit in the equations, but also in a simple case of a product. When you write down a product,
I agree.
Then you see it, and then it gets to your mind the fact that by a mirror symmetry you have a coproduct. And you only get there by symmetries and understand that. I think the analogy can be made, really, with the role of symmetries in equations in physics. They know, our colleagues, that symmetries correspond to conservation properties. This is the beautiful work of Noether. So they would never say that, the equation, because the symmetries are implicit, is what you know. Pulling out symmetries from equations is a fundamental job, and I think this is a major point in favor of category theory with their foundational role. I mean,
I agree. I fully agree. I only meant there are situations where, if you, for example, want to follow how to, equational things like cancellations and so on, and arguments, the argument, let's say, from x plus 1 isomorphic to x to extracting a natural number object is diagrammatically is very messy. But in general, I absolutely agree with you. I mean, of course, because the fundamental the notions that are precisely those notions in a way which, as you say, which do allow natural symmetry, where the symmetry springs to the eye. There's some one-way arguments. You see, of course, like the argument going, where a computation or something goes on, which is essentially in one direction, where typically diagram arguments don't actually prove to be so simple to use. But I think those are probably those situations in which there isn't a rather evident symmetry. Yeah, that would be my guess.
Yeah, concerning not only constructivity but also predicativity.
I knew that would come up eventually.
No, is there some possibility to translate, at least partially in topos theory, some aspects of Nelson's predicative arithmetic or not?
I haven't really thought about that. No, I'm not sure.
Because you have a succession of induction.
Yes,
stronger and stronger.
I don't see why one can't do that.
One is bounded in
Yeah,
but I don't. But I don't see why one can't do that just in general, in an intuitionistic setting, at least in principle. What I mean is, you don't really need. I don't know. You do it with certainly with arithmetic. It would seem very likely that you would be able to present. I haven't done it, but predicative arithmetic or systems of predicative. Well, that's been considered also by Pfefferman. He has, there are predicative systems of predicative arithmetic that he's considered, which you can, which can be presented intuitionistically. So I would guess so.
The interest of those tops, the Italian tops, it accommodates beautifully in predicative.
Yes, that's right. That's right. In fact, that is a problem. I think a sort of contemporary problem, because the work in computer science and sort of stuff in type theories is coming, ultimately from originated really with Martin Löf and others, mainly with Martin Löf, is predicative. And this is in particular the fact that predicative and it doesn't have extensionality built into it, and there are all kinds of things that you take for granted, of course, even in the topos setting, in the local set theory, that you can't take for granted, right, in the predicative setting or in a setting coming from type theory, and actually trying to sort all that out, is something that is now actually being undertaken. In particular, the thing that interests me lately was has done for some time, is why is it that if the axiom of choice implies the law of excluded middle, right, in the usual, in intuitionistic set theory, topos theory, Diocanescu's theorem, then why is it that in the case of Martin Löf type theory, the axiom of choice is affirmed, but you don't have the law of excluded middle? So where does it break down? Well, finally, I think we have an answer to this, but it's not so much to do with predicativity there. It's to do with extensionality. It's another issue. Well, I think intentionality and extensionality are the other. Predicativity and impredicativity, one axis, if you like. And intentionality and extensionality is the other. And intentional mathematics hasn't really played. Well, it's natural in computer science, of course, because there you're just given the program. You're not given the extension, the function. You're given the intention. But in mathematics generally, it's been extensional. That was the whole point of set theory. And it's been difficult to sort of detach, I think. Impredicativity has also, that's another one that's come up. But I think extensionality and intentionality are at least as important. Anyway, sorry, it's not.
Can I just put in a
sorry.
plug here for the work of a very old mutual friend of ours, Alberto Peruzzi.
Oh, sure.
Who wrote a very nice little paper about the forms which extensionality principles
yes,
took
I
in
remember
topos
it.
theory,
yeah.
And their relationship with the various forms that the axiom of choice takes, and carried out, I thought, an extremely nice taxonomy of the various strengths of extensionality principles in topos theory, showing particularly how some of them are deeply connected to topological properties of the topos, like relative uniform separability. And anyway, just wanted to mention that.
Yes, it is rather. Well, it's coming back. It's it's stepping onto, getting closer to, to central stage now, I think.
Actually, I have I think, related question concerning what you call the amorphous objects and this discrete structure, because I think there is a problem here if we try just to start with this approach, because after all we should distinguish between objects and topos, say which morphisms are composable, which are not, which diagrams commute, which are not. And the question is whether probably is it possible and interesting or probably not. Just try to to push this approach a little bit further and say think topos not as an extensional class, but say something like intentional object. And
most of this stuff, the stuff on amorphous sets and these what seemed rather curious features at first of objects in the free topos and in the effective topos. Don't seem to have. I mean, they arise really from essentially from thinking of objects as computable in some way. I mean, they don't. You make these analogies, which I think one can make the analogies, which are very nice, and you talk about clouds, and you think of. But I'm not sure how myself. I mean, how reliable, if you like, those those sort of analogies are when you try to transfer them, let's say, to physics. See, one point I would make is that in the case of the smooth topos, right? Yes, it has these, it has very few exotic features. Actually, it is the universe in which differential geometry. But the whole point of it is that the tangent bundle is representable. I mean, that's the whole idea. It's got, and so naturally you're going to get the objects that you have there should correspond very naturally, right, in some way to intuitions about smoothness and geometric objects, and they do. There's no question. They really do. You can write a whole book on doing physics, base elementary physics. I do Euler derivation of the Euler's equations of continuity. You can always read it off from Euler. Just using these, and it's very close to those intuitions. Now, on the other hand, in the case of the let's say the free topos or the effective topos, where one does have these rather peculiar types of set, this relation between the natural numbers and power sets or whatever. These are rather stranger universes. I mean, nobody had really thought of universes in which everybody thought in the past about universes. Everything's smooth. That's where you did physics. Nobody. It was completely unexceptionable, right? Thinking of a universe in which every function is computable, on the other hand, I mean, that was not something that had. That's a more modern development, and it sort of emerges, oddly enough, through Brouwer. Although Brouwer wasn't really concerned with computability as such, it was just that he was concerned with constructive evidence, the intuitive evidence. And of course, in mathematics, there is a connection between intuitive evidence and computability, right? I mean, so I think it was really those features that emerge, if you like, in the effective, certainly in the effective topos, which are, harder to assimilate, if you like, to let's say to physics, or at least to the image. I don't know. One really interesting thing is that none of this stuff has been applied to quantum theory. There's no quantum topos. Nobody even knows what a quantum object really is at the categorical level. David Finkelstein keeps publishing these extraordinary works where which are very interesting, but he doesn't have a decisive answer. There ought to be a quantum topos, you see. There ought to be, not discrete. There are actually four, right? The discrete is, it's the category of sets. That's the pure sets. I wanted to talk about that sometime too. Recursivity in the effective topos, smoothness in the smooth topos, and minimality. Minimal constructivism in the free topos. Where's the quantum case? Because nobody seems to know what a quantum object should be at that mathematical level, at that very basic level. One does know what a space is, right? I mean, you can axiomatize it more or less, but a quantum ensemble I've not seen any decisive description of it. At least you can't seem to fit it into a categorical framework in a natural way. Well, I know efforts are sort of being made, but at the quantum topos, that's what we really need. Sorry, yeah. Thank you. Yes. Thank you very much.